Welcome back to Mechanical Engineering Made Simple.
It's good to be here.
Today we're looking at something that, honestly, most people drive past every single day without giving it a second thought.
Oh, yeah.
You see them at refineries, chemical plants, maybe even behind a large brewery.
Yeah.
Big steel tanks. Silent, stationary. They look pretty boring.
On the surface, sure, they just look like big metal buckets sitting in a field. But if you look closer, those tanks are actually pressurized vessels. And that changes everything.
That is the hook for today.
Yeah.
Because while they look simple, the source material makes it pretty clear. A pressure vessel is essentially a ticking time bomb that we've managed to tame.
Tamed with a whole lot of math and physics. It's a dramatic way to put it, but you're not wrong. The potential energy stored inside one of those it's immense.
Right.
You're compressing gas or liquid to hundreds, sometimes thousands of PSI. You are taking a massive amount of energy and trying to hold it inside a thin metal skin. If that design fails, it doesn't just leak. It can result in a catastrophic energy release. We're talking shock waves that can level buildings.
Which brings us to the central conflict of this deep dive. It seems like engineering these things isn't just about making it strong. It's this constant cage match between two forces, safety and economy.
It always is. See, you could make a pressure vessel infinitely safe. It's actually easy from an engineering standpoint. You just make the walls 5 feet thick.
And it would never burst.
Never. You could shoot it with a tank and it wouldn't burst, but
I'm guessing you'd go out of business trying to build it.
immediately.
Yeah.
It would be so heavy it would sink into the ground, and the steel bill alone would bankrupt the project. So engineering is the art of finding that sweet spot.
Thin enough to be affordable, but thick enough not to kill anyone.
That's the job.
And to find that spot, you need a rule book. Or, as the note suggests, a really expensive calculator.
Yeah. Usually both.
Let's unpack that. The Bible for this seems to be the ASME code, section 8. But there's this fork in the road right away. You have Division 1 and Division 2. To an outsider, that just sounds like bureaucracy. What's the actual difference here?
It's not just bureaucracy, it's a business decision. Think of Division 1 as design by rules. It's the old school cookbook approach.
Okay, so it gives you the recipe.
It gives you explicit formulas. You plug in your pressure, your diameter, your material, and it spits out a wall thickness.
Okay, so it's fast. Plug and play.
It is efficient, but because it's a one-size-fits-all approach, it has to be conservative. It uses a higher safety factor to account for stresses we aren't explicitly calculating.
So you're adding extra metal, just in case.
Just in case there are forces at play that the simple formula missed. You save time on math, which means fewer billable hours for the engineer, but you spend more money on the actual steel plate.
Right, a penalty on the design for taking the easy route.
Exactly. Then you have Division 2. This is design by analysis.
The expensive calculator.
The supercomputer, more likely. Division 2 lets you use thinner walls, less metal, lighter vessels, cheaper fabrication. But in exchange, the code demands you prove it's safe through rigorous analysis.
So you're talking finite element analysis, fatigue studies, all of that.
Oh yeah, you're getting into the weeds of the physics. You're trading metal for math.
So if you're building one small propane tank, you just use Division 1 and buy the extra steel because hiring a team of analysts is too expensive.
Exactly. But if you're building a massive reactor that weighs 400 tons, the cost of that extra steel is astronomical. So you pay the engineers to run the Division 2 analysis to shave down the thickness.
It makes sense. It's like bizzing a suit off the rack versus paying a tailor.
That is a great analogy. One uses more fabric to fit everyone, the other is trimmed perfectly to fit just you.
Okay, so let's get into that math. Stress analysis. The text makes an interesting point that I struggled with a bit. It says the goal isn't to find every stress.
No, that would be a waste of time. A vessel has infinite points of stress. The goal is to find the governing stresses, the specific ones that actually dictate how thick the plate needs to be.
And the notes break this down into two main flavors, membrane stress and bending stress. Help me visualize membrane stress.
Picture a balloon. When you blow it up, the rubber skin stretches evenly, right?
Right.
That tension, that pulling apart of the fibers along the surface, is membrane stress. It's just stretching.
But steel isn't rubber. It's rigid. It fights back.
And that's where bending stress comes in. This happens at structural discontinuities.
Yeah.
Think about the corners where a head meets the shell or where a nozzle sticks out. The shape changes, and the metal has to bend.
Okay, so membrane is stretching, bending
Yep.
is, well, bending. But here's where it gets nuanced. The notes talk about a thin wall assumption.
Yes. And there's a specific check for this. It's the radius to thickness ratio. We look at R sub m over T.
R sub m over T, okay.
If the radius of the tank is more than 10 times the thickness of the wall, we call it a thin-walled vessel.
Why 10? What's magical about that number?
Because it simplifies the physics. If it's thin-walled, we assume the stress is biaxial. It's only pulling in two directions, lengthwise and around the girth. We get to ignore the third direction.
The radial stress, pushing into the wall itself.
Right. In a thin wall, that squeezing stress is so small compared to the stretching that we ignore it. It's a fly landing on an elephant.
But if that ratio drops below 10,
Yeah.
if the wall gets really thick,
Now you have a thick-walled vessel. And now that squeezing stress becomes significant. It's no longer a fly, it's another elephant. The stress state becomes triaxial, and the math gets much, much harder.
so Division 1 just kind of assumes you're building thin walls.
It does. If you're building a cannon barrel, Division 1 formulas simply won't work for you.
Okay, so we know how the stress is distributed. Now, how do these things actually die? Because my movie brain thinks huge fireball. But the source material says failure is way more nuanced.
It is. We use failure theories for this, and again, it splits Division 1 versus Division 2.
Division 1 uses maximum stress theory. What's the logic there?
It's the oldest, simplest theory. It basically says failure happens when the pull in any one direction hits the material's yield point. Imagine pulling a piece of chalk from both ends.
Eventually, it just snaps.
Exactly. It's intuitive, but it assumes the material is brittle, like chalk. Modern steel isn't. It's ductile.
Which is why Division 2 uses maximum shear stress theory.
Precisely. Ductile materials don't just snap, they slide, they yield. This theory assumes yielding starts when the shear stress reaches a critical point. It's like sliding a deck of cards. The failure happens at a 45-degree angle.
So the molecules are sliding past each other.
Correct. And calculating for that sliding failure is much more accurate for the ductile steels we use today.
So knowing how we predict it, what are the actual real-world failure modes?
Well, beyond bursting, you have elastic deformation. The vessel gets too bendy or buckles. Then there's brittle fracture.
The text mentioned that with hydro tests. That sounded scary.
It is an engineer's nightmare. Steel gets brittle when it's cold. If the water you use for testing is too cold, say 40 or 50 degrees Fahrenheit, and you have a tiny flaw, the vessel doesn't stretch. It shatters, like dropping a glass vase.
A massive steel vase? That's terrifying.
It has happened. Then you have excessive plastic deformation where it just stretches and doesn't bounce back. And finally, fatigue. This is the silent killer.
Cyclic service. So filling and emptying over and over.
Pressurizing and depressurizing. It's like bending a paper clip back and forth. You do it 100 times and it snaps.
And the notes highlight that bad design details can cut your strength in half here.
Oh, easily. We call them stress razors. Sharp corners, bad welds. In fatigue service, those little details are where the cracks start. The vessel doesn't fail from the general stress, it fails at that local concentration.
Okay, we've covered internal pressure. But there's another enemy, one that seems even sneakier, external pressure.
The invisible crusher.
This is usually vacuum, right?
Yeah.
The tank is empty and the atmosphere is trying to crush it.
Correct. Or it's jacketed with steam pressure on the outside. And the physics are completely different. Internal pressure makes a vessel stable. It wants to be a circle.
External pressure wants to flatten it.
Exactly. And here's the surprising fact. A vessel under external pressure can fail substantially below the yield strength of the material.
How is that possible?
Because it's not a failure of material strength.
Yeah.
It is a failure of geometry. It's called buckling.
The soda can analogy.
The best one. Take an empty soda can. You can stand on it if it's perfectly upright, but tap the side just a little.
And crunch. It collapses instantly.
That is buckling. It's an unstable state. And for external pressure, the length of the cylinder matters immensely. A long cylinder is much easier to buckle than a short one.
So if you have a 100-foot tall tower under vacuum, how do you stop it from crumpling?
You cheat. You add stiffening rings around the outside.
Ah, the hoops you see on those towers.
That's what they're for. They're structural cheats. They act as boundaries, so the physics doesn't see a 100-foot tower. It sees 10-foot towers stacked on top of each other. You chop the effective length down.
That's clever. Okay, another invisible threat, the cold. We touched on brittle fracture, but let's talk about the design parameter, MDMT. Minimum design metal temperature.
This is a huge battleground in design.
A battleground. Why?
It's about money. To prove a metal is tough enough at low temperatures, you have to do Charpy impact testing. You freeze a sample and smash it with a pendulum.
That sounds expensive.
Very expensive and time-consuming. So the goal for many designers is to play the exemption game.
I saw the charts in the notes. How do you win this game?
You have a few levers. You can upgrade the material, or, and this is counterintuitive, you can increase the thickness.
Wait, making it thicker helps avoid testing. I thought thicker metal was more prone to brittle fracture.
It is. But if you make it thicker than required, the stress in the metal is lower for the same pressure. Lower stress means you're further from the danger zone, so the code lets you operate at a lower temperature without testing.
You're buying your way out of the test with extra steel.
Exactly. And there was one other loophole that really caught my eye. Stress relief.
Post-weld heat treatment.
Yeah. Even if the code doesn't require you to bake the vessel to relieve welding stresses, if you do it anyway, the code rewards you. You can reduce your minimum allowable temperature by 30 degrees Fahrenheit just for doing that.
So it's often cheaper to cook the tank in a giant oven than to run all the tests.
Often, yes. It's a game of trade-offs.
Okay, let's step back and look at the vessel as a structure. These things are sitting outside, exposed to the elements.
Right. A tall tower isn't just a tank. It's a cantilever beam stuck in the ground. It has to resist wind and earthquakes.
I was surprised wind isn't just about pushing.
No, that's the static part. The dangerous part is dynamic. You get vortex shedding. As wind flows around a cylinder, it creates these alternating swirls on the backside. It pushes left, then right, then left.
Like a flag flapping.
Exactly. And this can make the tower vibrate. If that vibration matches the tower's natural frequency, you're in real trouble.
And there's a ratio for that, too.
If the height to diameter ratio over D is greater than 15, you have to investigate that dynamic stability. The wind could literally shake the vessel apart.
Wow. Now, what about where it meets the ground, the skirt? What if the vessel is at 800 degrees?
And the skirt is anchored to concrete at 60 degrees. You have a massive thermal fight at that weld. The vessel wants to expand. The skirt wants to stay small. The weld will rip apart.
How do you fix that? The text mentioned a hot box.
It's a clever, simple solution. You build an insulated chamber at the top of the skirt. It traps heat from the vessel itself to warm up the top of the skirt.
So the top of the skirt gets hot and expands with the vessel.
Right. It creates a gentle temperature gradient instead of a thermal shock. It saves the weld.
Smart. What about horizontal vessels, the propane tanks? They sit on saddles.
Right. And you can't just rest a heavy tank on a concrete block. It would puncture the shell.
So how big should the saddle be?
The optimum is generally 168 degrees. It wraps almost halfway around the bottom and distributes the weight perfectly.
And I saw wear plates mentioned.
Yes. You don't weld the rigid saddle directly to your pressurized shell. You weld a wear plate to the shell first. It's like a second skin that distributes the load.
Okay, final segment. The weight of steel. You'd think with all this math, we'd know exactly what these things weigh. But the text says the calculated weight is always less than the real weight. Why?
Several reasons, but the biggest is plate overage.
Overage.
Steel mills are businesses. If you order a half-inch thick plate and they roll it to 0.499 inches, you'll reject it. It's out of spec. So they always roll it slightly thick to be safe.
So you're paying for steel you didn't technically ask for.
And lifting it. Then you have thinning allowance for the heads, the curved ends.
When you shape it, it gets thinner.
Right. So to get a 1-inch thick head, you might have to start with a 1.5-inch thick plate.
That's a lot of extra metal.
It is. But here's the kicker. The heaviest the vessel will ever be is usually during testing.
The water trap.
Right. We test them by filling them completely with water. Water is heavy, often much heavier than the gas or oil it will eventually hold.
So if you design the foundation just for the operating weight,
you are in for a bad day. The moment you fill it with water for the test, the whole thing might sink into the mud or collapse the supports.
that sounds like an incredibly expensive mistake.
It's a classic rookie error. You have to design for the wind, the cold, the vacuum, the pressure, and even the water you use to prove it works.
It really is a balancing act.
It's a compromise between internal pressure trying to burst it, external pressure trying to crush it, heat trying to expand it, and the accountant trying to make it cheaper.
And the engineer is sweating in the middle.
Always.
Next time you drive past a refinery or chemical plant, realize those tanks aren't just static metal buckets. They are carefully engineered balloons, constantly fighting the urge to either burst or crumple.
And luckily for us, the math usually wins.
Usually. If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.
See you next time.